OpenAI is expecting to lose $14 billion by 2026. These large LLM operators need a more cost-efficient way of operating.
AI is very complex because at the top layer, it looks very easy and simple, that it's a steady power consumption. It's not. It's actually a very spiky power consumption. Bitcoin offers a very good platform for that because when you think about Bitcoin, you can overclock and underclock at will. This is very powerful. Now you can utilize the idle time of these workloads when they're not consuming power and use that for Bitcoin.
If we can make LLMs more energy efficient, then those LLMs will have a cost advantage, which will give them a market share advantage.
That's right. So we are sitting at the brink where MARA can play a very important role in creating energy efficient LLMs. This will be a genetic marker in how large language models will be adopted in the industry over a period of time.
Janet, I'd love to welcome you to MARA's board. We're so happy to have you join us. I'm very proud. You have an amazing background in the industry, and I'd love for you first maybe to share with the audience your background and how it's relevant to what MARA is doing.
All right, very good. So I have about 2.5 decades of experience in the field. I started out as a computer scientist, a practitioner in the field. So early days, I did a lot of AI, but then quickly went into data centers. And then in data centers where cloud was born, I was at that edge where cloud was born. And then we started to see the intersection of AI, data centers, and then energy. So this brings me to full circle, to really come here at this point of time and to be sitting at this intersection of all three coming together.
It's such an exciting time. As we look at these fields all coming together, the world of data centers had their first real explosion during the internet boom in the early 2000s, and you were obviously part of that. And as we now move forward, it seems the key constraint in a lot of this is energy.
100%.
And so as you look at the world of AI, hyperscalers, data center, and then you look at Bitcoin mining, where do you see synergies? Where do you see an overlap? And where do you see the opportunity for MARA?
This is a very, very good question. And I think that for the first time, we have recognized that with AI in the data centers, with electric vehicles, with energy, all these players have to start to cooperate, because we have reached an unprecedented level of energy consumption, especially with the large language models and generative AI. We have to lean into players that can help us. And Bitcoin has also been one of the energy consumers. So all of the energy consumers have to come together, first of all, and then we have to figure out the other end, the back end. Are we consuming this energy in an efficient manner? Right? Is there waste or not waste? And how do we do that? So at this point of time, I think we have once in a generation lifetime opportunity to transform the energy landscape as we know it.
So many marketplaces, many industries have been transformed over time. You and I were speaking earlier in a conversation how Amazon transformed the whole model for commerce and book selling. That's right. How do you view that applying to the energy sector?
Yeah, I look at where MARA is at right now, and I look at the energy sector, and I feel like we need an intermediary that can really look at the consumption model of energy and make sure that there is no waste in that. So we don't have democracy in energy. We have democracy or have democratized commerce. So Amazon made no distinction between buyers and sellers and the payment cycle. So it's independent. People can do that. We don't have that in energy. So in energy, we don't have a steady state workload basis. We have spikes in energy. We have a lot of waste in energy. And we're not able to transform with traditional energy infrastructure. So we need transformations in multiple areas, if you will.
So essentially, the vision would be to unify these varying workloads, whether it's consumer loads, whether it's AI workloads, whether it's traditional data center loads, whether it's factories or buildings, and layer together with those workloads other workloads that can vary synchronously with them. Yes. So essentially marrying the workloads to provide an even consumption that is much more efficient to the marketplace.
100%.
And so on the provider side, the energy generation side, their key challenge is they want to have a levelized demand because that's how they manage their business. On the consumption side, you want to have always access to the power you need and not be restricted. And so there's an opportunity for a layer between those two
100%.
that sits between them and provides this balanced load. On the one hand, balanced to the grid. On the other hand, always available energy to the consumer layer.
Yes.
And you and I were talking about before how MARA's role could play there and what MARA could do.
Yes.
Share me a little bit more kind of your thoughts there.
Yeah. So if you look at what happened to the data centers way before cloud existed, right? We always had heterogeneous workloads. So the application workloads were tied to the compute infrastructure, was tied to memory, and was tied to many other, it was all tightly coupled, if you will. That coupling cost us a lot. What do I mean by that? So when the application changed itself, or if the compute needed to be upgraded, we had to change the whole stack. We didn't decouple them. And with cloud, we now have a pool of compute resources. We have a pool of storage resources. We have a pool of memory resources. So these heterogeneous workloads can come in, and if one compute dies within that pool or one memory dies, it's still pooled. So Gmail is always on. Many of these applications are always on. Energy is in a similar state. Right now, it's very coupled. And MARA as an intermediary can decouple this consumption model, right? And so because it's not tightly coupled, we can be the right load balancer for where this energy needs to go based on the heterogeneity of the workload, right? And then we can also take AI, and when we look at AI inherently, AI is very complex because at the top layer, it looks very easy and simple, that it's a steady power consumption. It's not. It's actually a very spiky power consumption underneath that steady, how the resources are allocated, what the memory is being used, the encoding and the decoding. So if we can have a fine-grained control over the usage of energy pattern, power consumption within that structure, I think that's incredible. We will be able to curb waste. We can get to a regulated form of energy, and steady state, we'll have a very good steady state of energy in terms of its consumption.
Excellent. What's exciting about that to me is essentially we would be building and delivering an abstraction layer
100%.
where you're abstracting demand from supply.
That's right.
And the unique thing about leveraging Bitcoin mining is it's this hugely curtailable load.
Right.
So we essentially go from an industry where you have these varying workloads,
Yes.
like AI,
Yes.
to where now you have a variable
Right.
demand load.
Right.
And so by marrying the two, we essentially create a very homogeneous power profile to the grid.
Yes.
That's super exciting.
Yeah, and Bitcoin offers a very, very, very good platform for that, because when you think about Bitcoin, you can overclock and underclock at will. This is very powerful because now you can utilize the idle time of these workloads when they're not consuming power and use that for Bitcoin. So you can do the whole Bitcoin operation with that zero cost. Right? So that is an added opportunity over there. With the abstraction layer brings many benefits, but one of the benefits is you have steady state, and the usage pattern becomes very monitored and becomes essential usage pattern, not a usage pattern. It's not like a reserved instance on an Amazon cloud, whether you use the instance or you don't use the instance. You actually know it's a reserved instance, but here's your exact usage pattern. And so you're able to divide and conquer much better with the energy.
And what's exciting with this is when you talk to data center operators, when you talk to hyperscalers, they get this.
Yeah.
They totally get it. The interesting thing is the energy companies
Yeah.
are still not sufficiently sophisticated in their thinking about this. And so one of our challenges is obviously to educate them on this. As I look at the energy workloads in the data centers, and you mentioned this concept of zero cost energy, we believe that providing Bitcoin mining as a service to balance workloads is a route to zero cost energy for Bitcoin mining. Essentially, de-leveraging the energy consumption of Bitcoin mining and instead turning it into a resource.
Absolutely.
And so if we flip the story in that way and we look at Bitcoin mining providing a service to all these workloads,
Yes.
it essentially Bitcoin mining becomes a service provider.
That's right.
And we get paid for that service. And one way we get paid for that service is through consuming that wasted energy
That's right.
that otherwise would just not be used.
Yeah. Yeah.
And so it makes for a very exciting future for MARA because now all of a sudden you see this marriage of Bitcoin mining, data centers, hyperscalers, and AI, which is a very exciting future, I think, not just for our shareholders, but for the data center industry as a whole. Janet, one question that obviously many people are curious about is, what attracted you to joining MARA's board?
So there were three things that went into my decision making to come to MARA. The number one factor for me was MARA as a company and its position at where it sits right now. Incredible momentum, incredible growth, and incredible value. So what do I mean by this? So when you look at AI, you see how AI is fundamentally changing the future of work. And what I mean by that is we are moving from being actually people that do the work to orchestrators of work. And this is all very dependent. This dream of being the future of work and the orchestration of work is all powered by energy. So MARA plays a very pivotal role in that. And so that was very, very interesting for me. I think that was my number one factor. And then my number two factor was really about the people. I was very excited when I met you. I was very excited when I met the team. I think the teams are the ones that the intellectual property of any company is really the team, because that's what takes the company where it needs to go. And so I was super excited about the people I met and the people I talked to. And then the third factor that went into my decision making was what intrinsic value could I bring that is sustained over a period of time. So sustainable value that I could bring to the table. And I felt that all three of those matched for me in regard to MARA.
Well, I think you are the perfect match for MARA. Not only do you bring an amazing set of skills and experience, but in the little time you and I have spent together, the alignment around vision, the alignment around the future, and the alignment about the opportunity couldn't be better. Talk to me a little bit now also about the concept of heat in data centers and how do you deal with heat in data centers?
Yeah. So before you go into the heat, you sparked a lot of thoughts. So I'm just going to go into a few of those, right? I think one of the powerful statements you made, and this is, we talk about heterogeneity in the workloads, but there's also heterogeneity in the energy characteristics, right? Because it's coming from wind, solar, many different sources of energy, and the traditional companies don't know how to deal with the heterogeneity on the energy side. This is where I think, again, MARA can play a very interesting role. You can handle and do the mapping between the heterogeneity on the energy and the heterogeneity on the workloads, or the energy on the demand side, right? What kind of demand is coming for the heterogeneity of energy and from the different sources and the characteristics. Okay, so once we complete the front end, the input, now we go to the output. So with all of this power consumption with AI, we are seeing unprecedented heat being generated in these data centers. The heat, when I've lived and sat in the data centers, it's unbelievable how much heat these data centers generate, right? And when you think about entire buildings in the world, these data centers could power from simply just tapping into that heat. It's unimaginable that we waste that much heat. So this is another role we can play with immersion cooling technologies, the brand new technology, two-phase technology, where we are not dependent on water and other sources, but really be able to cool at very high capacity, and then to be reuse that power to go do useful things like heat buildings, and then bring the cost down for consumers in the end. Right?
Yeah, absolutely. If you think about a traditional air-cooled data center, you are using air to extract heat from the equipment, and then you need to use energy to extract that heat from the building.
Yeah.
If you then move to traditional immersion cooling, single-phase immersion, you have a lot of mechanical load or energy that you use to pump the liquid around, and then it has to be cooled. But in two-phase, you don't have that issue. Yeah. And two-phase solves a lot of other problems, one of which is an excellent way to capture heat and reuse it. In the future, it's fully feasible that data centers could be the primary source of heating for buildings, for factories, for residential communities. I could foresee a future where there are small data centers in buildings, where essentially the energy going to run the data center provides the benefit of the heat.
100%.
And so if you anyway have to invest in energy for a data center and energy for heating, and you can eliminate one of the energy needs because of the complementary nature of the two, that would be a huge energy saving on a global basis, because I think HVAC or heating is most probably 20% of all the energy use in the world today is for that purpose. But let me ask you, why would people want to put data centers in buildings? Why would there be a need for so many data centers spread all over?
Yeah. Imagine also the cost that is required to maintain these HVACs. At the end of the day, the building owner or the homeowner does not just want the house to be heated. They don't want to worry about regulating that heat. They don't want to worry about regulating cooling. They don't want to regulate heating. They don't want the maintenance aspect of it. But if the data center is really the one that's consuming the energy, and as a byproduct, we then go heat houses and homes, it's a total win-win situation. I also think that we need decentralized data centers, right? And we need decentralized data centers because we are going to the edge. And in the edge, we can't have a centralized computing. We have to have a layer of computing that is separated from cloud, which is the centralized computing. So when we talk about fog or we talk about edge layers, we're looking at decentralized data centers. And in these decentralized data centers, we're also looking at bite-sized chunk loads of workloads that are smaller, coming from sensors and other IoT devices. And the use cases that we're seeing in the edge are very different from the use cases that are being monitored. So that's another incredible opportunity as we move towards, ubiquitous digital everywhere. And we integrate energy as part of that, a key component. We've got to start to think about decentralized data centers, smaller data centers, different locations, but centralized compute, if you will. Or somewhat centralized compute between the cloud and the edge.
So by the same token that one has an abstraction layer between the power consumption and power generation, in the world of AI, there will need to be an orchestration layer 100%. That can essentially load share these workloads spread amongst lots of micro data centers.
Yes.
The advantage there, I can imagine, is that where in a traditional hyperscaler large-scale data center, it's 5 nines, you need redundant power, you need constant uptime. Yeah. If you're able to load share and essentially spread the workload across data centers, similar to how RAID technology works in the storage industry with hard disks, you could lose a data center and the workloads would just reallocate and 100%. Shift. And so now data center operators wouldn't need 5 nines anymore.
100%.
Which dramatically lowers the cost of these data centers.
Yes. And you've sparked a whole lot of thoughts in my head right now, right? And I'm really thinking about how we go back to this heterogeneous nature of workloads. So let's go touch upon that a little bit. When we think about the workloads at the edge and we think about this, trying to load balance with this abstraction layer where the workloads need to go. So maybe how the distributed brain came into existence before there was a central brain, right? You think about researchers, when they wrote papers, they wrote a single paper, and there was like a group of people that were experts and then rated that paper. Today we have distributed brain, Mechanical Turk. We are using distributed resources to really figure out how to get the job done. So think about that abstraction layer, which then says, I know I'm the Kubernetes, I'm the orchestration layer. I know how to orchestrate where these workloads should run, given we understand its energy requirements. We understand the consumption patterns, all of these things. So that MARA has that opportunity to be even the orchestration layer between all of this. That's very, very exciting, right? And even orchestrate between, and you can do it autonomously. So you can even tap into AI models to say, we now the orchestrator, because we control energy or want to understand the efficiencies in energy. So where do we send the workload based on the energy needs, not just based on the latency or the throughput? You also deeply understand how to promote and demote, right? Because of the idle time usage. So now you have the concepts that we built in cloud around storage, right? If you're not using storage as much and you have reserved a certain storage, you can demote that, or you can promote that, or you can bring visibility to that which is closed, right? The other thing, I think that when we started talking about chips and AI and workload, the forefront of our mind was always throughput and latency because we talked about performance. Now we have this third equation, and this is energy. And energy has actually become higher than throughput and latency, right? Because without energy and the consumption of it and the shortage of it, we can't actually have any benefits of throughput or latency for that matter. So that's another aspect is we've gone from third place to like number one place to do the orchestration, right? And we uniquely sit in that position where we can own.
Absolutely. It's you can think of the data center design, if you would, as being energy first.
That's right.
And how are you going to orchestrate the distribution and utilization of energy? And then the workloads you put into that data center follow.
Yeah.
As opposed to you're designing something with a certain amount of throughput and capacity. So as you look at this distributed workloads, energy is obviously this core component, and managing that energy component becomes very important. What other infrastructure do you think is important? Networking, things like that.
Yeah. I think this whole, earlier we touched upon this transportation of energy, like transmission, coordination, there's a lot of waste in that, right? And so if we can, that supply chain, again, MARA's role in that supply chain where all of that waste is curbed becomes super critical, because right now the process is very fragmented, and because of the fragmentation, there is loss at every stage. So unifying that fragmentation, unifying the loss becomes critical. Now, I'll also go a little bit deeper into large language models. Now, today, when you think about large language models, not all large language models are equal. They're slightly different. And when you think about how the transformer is working with its encoding and decoding, right? So when it encodes, it needs a lot of power. And this is to your point about inferencing. When it's encoding, it needs heavy compute. But when it's decoding, so encoding is we are saying, we've got a tail query, for example, and the tail query could be Jaguar. Is it a car? Is it an animal? What is it, right? And so now we need to query substitute to really figure out what is it, what is the Jaguar. And that's what we do when we do the encoding. Now, the decoding is very simple because now we've learned what the Jaguar is and we're decoding that. It's not heavily dependent on compute. It's heavily dependent on memory. Right? So now getting to that fine-grained level of understanding the usage pattern. Now, CPUs have done this very well. GPUs have not. GPUs, it's like you send everything to the GPU, it consumes a lot of power, and we don't know. So if you look at how many GPUs we needed in the early stages of AI, so the first stage of AI, we're talking decision trees, we're talking naive Bayes, that sort of, we needed few, I want to say 100, 200 clusters of GPUs. Now we get into the second layer. We're getting into neural networks. Now here it's a little bit deeper, second generation of AI. We need to understand images. We're getting into convolution neural networks. We need thousands of GPUs. Now we're getting to the third one, which is LLMs. We're talking tens of thousands of GPUs. When you're dealing with tens of thousands of GPUs, if you can't regulate at that decoder level, the waste is exponential. It's disproportionate as compared to where you understand the smaller workloads. So even in the large workloads where we've said, it just needs GPU, we think it's steady. If you peel one layer below, just the resourcing of the application, the decoding. So we're sitting at the brink where MARA can play a very important role in creating energy efficient LLMs. This will be a marker, a genetic marker in how large language models will be adopted in the industry over a period of time.
Yeah, because if you talk to LLM operators, as they look at power, they overdimension their power.
That's right.
And they only utilize 70% of what they think would be max capacity, and then they overdimension above that even.
That's right.
And so there's a huge amount of waste there.
That's right.
And if I think about what you just said, then MARA's role in optimizing the consumption of that waste.
That's right.
Because they're paying for that energy anyway.
For that energy. Yeah.
And so that truly becomes free energy.
That's right. That's right.
Which would enable MARA to essentially mine Bitcoin at zero cost.
Yeah.
Where Bitcoin is just the energy balancer.
That's right. That's right. And if, for example, somebody's, there are very risk-averse type of models, right? If a risk-averse model is there saying, I definitely want to sleep at night, so I want my reserved instance, whether I'm going to use the energy or not. But MARA can come in and say, yes, it's reserved for you, but you're not using. So I'm going to use it while you are at rest. Energy is being used while LLM is at rest or the model is at rest. And then I'm going to translate that to actual return on investment for you. I'm going to give you back cost. Wouldn't that be wonderful? Like I have all these AT&T minutes and I need them because I don't know if I will use them, right? But if I'm not using them and you return money to me at the end of the day saying, Janet, you have 3,000 minutes you didn't use, right? Wouldn't that be powerful? Right? So there's all kinds of utilization and optimization that can garner a very substantial revenue model there.
What's exciting about the AT&T minute
Yes.
analogy is you can't carry over your minutes to the next month with the energy, right? You have to consume it, and if you don't, it's wasted.
It's wasted.
Some estimates that our team has made calculate that the cost savings to the operator of an LLM would be upwards of 20% of their energy consumption. That is a huge number, an absolutely huge market. And so to your point, if we can make LLMs more energy efficient, then those LLMs will have a cost advantage,
That's right.
which will give them a market share advantage.
That's right. That's right.
And as we look at some of these companies today, there was an article recently that OpenAI is expecting to lose $14 billion by 2026. These large LLM operators need a more cost-efficient way
Absolutely.
of operating.
Absolutely. Absolutely. And to add to that, if you think about why we've already had a decade of big data, a decade, and we've had a decade of AI with the early stages, naive Bayes and all. Now we're coming into more sophisticated modalities, right? But are we going to take a decade for adoption of these modalities, or are we going to do it sooner? What's the linchpin there? It's energy.
Yes.
Energy is the linchpin that will decide the adoption curve, right? A disproportionate adoption upwards or disproportionate adoption downwards. This is the knob.
And as we look at the energy demand in the world, it's obviously growing, a lot of it driven by data centers. One of the biggest problems is distribution of energy, transmission capacity. And so it becomes really imperative, both for the energy transition and for AI to truly be able to scale, as you said,
That's right.
that we find more efficient ways of distributing energy, transmitting it, placing consumption, bringing consumption from the traditional market to the source of generation.
Yes.
Bringing consumption to the solar farms, bringing consumption to the wind farms, which in and of themselves are intermittent energy producers.
That's
So now you have a need for balancing this energy.
That's right.
And if you can marry workload balancing and spreading workloads,
Yes.
then that intermittent energy aspect becomes less of a critical negative factor
Right.
and instead becomes a plus because that's very low cost energy.
That's right. I love the aspect of, reducing spike and burst capacity to steady state. Steady state is very measurable. Steady state is very efficient. Steady state is very, capacity can be planned with steady state. So we want to achieve a steady state, but we can't with what we have at a starting point from a source, because there we have intermittency by natural state of being intermittent leads to that spike and to that outburst. I also think that this democracy with energy, and I'm calling it democracy with energy, we can call it any other term, is actually going to speed up the adoption of AI. In a very large way. And that means, cognitive automation being adopted by industries that could never foresee cognitive adoption, right? For example, drug discovery. This is a very long industry, and to be able to try to figure out, can we automate drug discovery? Look at hundreds of thousands of parameters that contribute to a generation of a cancer cell, right? Like, what can we do? And energy is the gating factor. So if we bring that democracy of energy and AI and really to figure out this cognitive automation piece, we can cure diseases, we can bring faster solutions, drug to market that can help deaths happening, and the new virus coming. We don't know what's the next virus that will attack us. So all of these things are linchpinning on energy, if you will. So energy is a big component in all of this. It's a trifactor effect in my mind.
Absolutely. An exciting thing also is just in personalized healthcare. What a lot of people are now only starting to realize is if there was a digital twin of each of us.
Yes.
So you have depth analysis, you use full body MRIs, you start using sensors like Apple Watches, these Aura rings, et cetera, and you're tracking telemetry. Essentially, your healthcare provider could have a digital twin of you.
Absolutely.
And know not only what drugs are you taking, so you could predict drug interaction issues, no dietary issues,
Yeah.
et cetera. And these digital twins are really AI instances.
Right. That's right.
And so you essentially
It's your
have
health avatar.
it's your health avatar.
Yeah.
That's a great way of saying
Yeah.
it. And so these health avatars then all of a sudden need to run all over the place as well. But it's obviously need for confidentiality.
Yeah.
You don't want them running in a big public cloud.
That's right.
And so you're going to want them running at the edge,
Yes.
which is going to be very important. Digital twins apply to everything.
Yes.
If you think about cognitive computing,
Yeah.
you're talking about adding a layer of observation and insight
Yes.
to every aspect of what we do.
Yes.
How we drive is already done by cognitive computing.
Yes.
Think about an automobile. It's 100 computing subsystems all interacting with each other
That's right.
and being controlled by a driver head end, if you would.
That's right.
Airplanes.
Yes.
But now you go to factories.
Yeah.
You go to healthcare.
Yeah.
You go to education even.
Yeah.
The ability to do a digital twin of a student and understand a student's learning curve, literally.
Yes.
And how do you accelerate that learning curve? How do you support that learning curve?
Yes.
Because every student is different. You and I were talking earlier about our children and the fact that every kid is different and they have different needs. As we get to this ability to have mass personalization,
Yes.
the need for AI will only grow at an even more exponential nature, which means the need to solve the energy problem
Yeah.
becomes absolutely critical. Because if we want this adoption, if we want this, let's call it utopian future,
Yes.
where we can really leverage cognitive computing and we can leverage AI for all of these great things, we need to reduce all the friction
Yes.
for the deployment
Yes.
and the ability to roll this out.
Yes.
And I think that's an area where MARA can play a very critical role.
Yeah. Extremely well stated. I think the friction is what's crippling us right now. And if we can remove the friction. I also like this concept of avatar because the personalization plays a very critical role. And in medicine, especially when you think about it, everybody's eating patterns, their genes, all of it is personalized. So you can't have generic medicine. And, we've done statistical kind of an analysis when it comes to medicine, and now we've also bought demographics. So we say statistics and demography, but it's really very personalized. Everybody's gene structure is very different. Everybody's dietary habits are different. Their lifestyles are different. And so to be able to use the digital twin to actually look at what and then predict, and that prediction can be life-changing. As you say, oh, I'm headed in this path towards the next decade. If the digital twin can help you that with your full body scan and all of that, it's extremely powerful. And then the role that MARA plays in creating that personalized medicine. And it's also personalized everything else because, our banking methods are personalized. Our habits of driving are very personalized. Some are defensive drivers, some are offensive drivers, some don't care. And as humans, we bring a lot of emotions. We talked about this, right? And emotions to some extent are very important because they operate at our primitive brain level, right? And at primitive brain level, when we use emotions, we're trying to figure out the lion standing in front of me, it's trying to eat me. I'm just going to primitive brain. I'm emotionally very bound to see how I survive. But tapping into your advanced brain, that's where the personalization comes in. That's where, you can get a little bit of a fine balance between the emotion and the non-emotion. Like if you were having personalized driverless cars that would drive just like Fred would drive and just like how Janet would drive, we'd never have an accident because we still adhere to certain standards, right? Defensive driving or leave the distance and show the, indicate before you change lanes and all this stuff. But so it's unique driving patterns. And yet there's a standardization and a uniformity. So there's no accidents, less deaths, no erratic behaviors, no somebody bringing in stress into their driving, right? All of these things become normalized.
Absolutely. There's an interesting concept that the telecom industry, especially in the mobile world, has been working with the automobile industry, which are called vehicle-to-vehicle networks. And so you think about all of these cars that are intelligent, driving along a motorway or driving along a street, you are provisioning and deprovisioning networks and clusters where all of these vehicles are able to interact and share data, right? There's a pothole ahead because the camera on a car 15 cars ahead has discovered it. So now your car's self-driving mode knows that. The car also knows what time you need to get to work, can look at the alternative paths, et cetera, and this mass personalization, if you would. needs to build on a huge communication infrastructure. And again, now we're talking about small data centers at every cell phone tower where this is happening. And I think as I look at MARA's role going forward, I'm excited about the orchestration layer of energy. I'm excited about the potential for orchestration layer of workloads. I'm also very excited about the ability for MARA to really play a role in the digital infrastructure that all of these micro data centers will have.
100%.
I think about liquid cooling. I think about redundancy, the ability for these systems to run and not suffer failures where they need to be human operated. And I get so excited about the technology we're developing around liquid cooling, around building mining technology or just compute technology that has much more redundancy built in. It's really almost going to the real-time compute world as opposed to the traditional commercial compute world and saying, okay, what do real-time systems need to be valid?
That's right.
And I think back to the days when I was working with supercomputers and IoT, and we're just seeing that now. And as you said, these things take time to adopt, but we're seeing this convergence now of sensor technology with the AI technology to leverage the insights, big data and the ability to analyze these large volumes of data, create inference, create digital twins that then allow us to do mass personalization. And it really lays out a future that's very compelling and very exciting, not just for MARA, but for the world, I think. So many people think about Bitcoin and they have lots of emotions about it. What happens if we instead look at Bitcoin from a rational perspective? Let's disconnect the emotional aspects of whether cryptocurrencies are good or bad and move away from that. And let's just look at Bitcoin rationally. In your mind, what is Bitcoin?
Yeah. So I look at it this way, right? I think you have to take a very neutral perspective, right? Bitcoin itself is really just an investment, right? But if you think about Bitcoin as a tool, or you think about Bitcoin as a platform, as an enabler, there's a much more larger potential. So you bring the neutrality into the equation and you say, here is a platform, a vehicle for us to tap into to become an enabler of the world we want to create in AI, in energy, in consumption, all of these things can be utilized. And I want to go more towards a platform versus a tool, because a tool is very specific, whereas a platform can have many tools or can have many applications of that. So if you think of that from a platform perspective, it just becomes an enabler. And I see the role of Bitcoin sort of neutrally in that. Right? If we don't assign the emotion to it, we can tap into the advantages and use the enabling function of Bitcoin to actually solve all of the big problems that we have in the world today.
And Bitcoin as a technology, the operation of the Bitcoin network, has benefits far outside of the financial enablement or the investment instrument. If you think about Bitcoin just simply as an energy consumer, it actually has benefits.
That's right.
It's dispatchable, meaning you can turn it off. And you don't lose value when you do that. When it's running, it's also generating value.
That's right.
Right? It's generating Bitcoin, it's processing transactions, it's creating value.
That's right.
And so there are very few technologies out there that have these properties of being dispatchable and generating large amounts of value. And I think this marriage of Bitcoin, again, and AI, this marriage of Bitcoin and energy orchestration, this marriage of Bitcoin and load balancing, and this marriage of Bitcoin and heat recapture and data centers and heat recapture, all get us to a place where we generate less waste.
That's right.
We optimize the waste and reuse it in ways so it's not wasteful. Being able to mitigate flare gas in oil fields reduces a considerable amount of methane that otherwise would be vented, because flaring methane is very inefficient from a methane consumption perspective. Being able to use stranded solar or wind assets. As I look at over the next few years and I think about what we at MARA are all focused on achieving, it's really a combination of reducing waste and energy.
That's right.
Reducing waste and energy consumption, and marrying the two in a way that realizes a dream
100%.
of better balanced energy load and consumption, less waste, and a faster enablement of things like AI.
100%. And when you say these things, I'm taking myself back to the time, again, pivotal moments in computational history, right? When we had single processors and the sheer ability to add threading to a single process, like these threads could go off and do other things. Or you think about parallelization, map reduce technology, right? You could reduce, map it out, and then reduce this. It's the same state that we are talking about, two sides of the same coin, the energy waste, the energy consumption, enablement, or abstraction, all of these things is that same sort of thing you're bringing into the energy world that we brought in the computational world a while back. Threading changed how we did computations, massively parallel computations, right? We're still in that same space, right? So I do think that technology does play a critical role in this change of structure.
We're also going into a different phase of technology where for many years we were building technologies that were kind of evolutionary.
Yes.
And then people like Elon Musk
Yeah.
applied kind of first principles and said, how do we build a car that really is software
Yes.
as opposed to a mechanical thing
Yes.
that a human has to drive?
Yes.
He has revolutionized space, or lift, as it's called, space lift.
Yes.
He has revolutionized some access to satellite technology. He's done a lot of amazing things. And I think we're moving into a phase where it's going back to these technology visionaries.
Yes.
Who see a big problem and want to solve it, but have to solve it in a vertically integrated process.
Yes. Yes.
And as I look at what we're doing, there's a lot of technology that we're developing. There's a lot of operational execution that we're doing. There's a lot of energy management. There's a lot of relationship management. And while on some level it could look to be very vertically integrated,
Yes.
in reality what we're doing is abstracting lots and lots and lots of different things.
Yeah.
And enabling the ability to orchestrate through those abstraction layers
That's
in an optimal way.
That's right. I mean, again, very powerfully stated, because when you're talking, I'm thinking about software-defined networking, right? What that did to us. Mm-hmm. Software-defined energy consumption. What MARA will do.
When you paint it that way, in my mind, that is the perfect kind of analog. Because software-defined networking enabled us to really provision and deprovision networks based on need
100%.
to optimize the use of all this network capacity so we didn't have all this dark fiber.
That's right.
Or we better utilize the dark
That's right.
fiber.
That's right.
You can think of energy just like dark fiber.
That's right.
And being able to do software-defined energy,
That's right.
load and consumption, right,
Yeah.
is a very...
And waste and the back end with it.
Exactly. It's a very exciting picture.
Yeah. And the other thing I'll tell you, I'm very passionate about waste, right? Because I feel like waste creates class structures, the have and the have-nots. And I think if we curb waste, we can have a little bit of equality, right? We can have a little bit of standardization. We can have a little bit of baseline threshold. Like we should not have poverty and just so many things in the world that can be curbed if we simply take care of our waste. And I think the faster we progress as a civilization, if we don't look at our waste, we will leave a larger waste footprint on the planet. So that's also a bigger goal that you have, is sustainable planet, carbon emissions. These things matter. And we can't move forward without having a look back, because history teaches us a lot. And so, this is like I like the feedback mechanisms, right? The feedback mechanisms is what makes AI models stronger, because we know where the gaps are, where the weaknesses are. And this feedback mechanism for energy is very important to understand the waste and how much of it is there.
And there's so much energy wasted in this world today. 40% of energy is lost in transmission.
That's right.
Just start there. Yeah. The experiment we're doing now with micro data centers in the oil fields with flare gas, capturing heat from data centers, and what we're doing in heating homes in Finland. Yeah. All of these pilots that we're doing are really experiments to understand how we can bring together more organized workloads. How can we orchestrate energy such that we can leverage it to minimize waste across those platforms? And all of the wasted or stranded energy that exists on this planet today. Just look at all the renewable energy that we have built in this west part of Texas, in the United States, that really is wasted because of lack of transmission and the fact that it's intermittent and that when it is most available is when the market needs it. And by being able to consume that energy and bring consumption to those places, we can eliminate huge amounts of energy waste.
100%.
And this is just the beginning.
100%.
One of the things with the AI industry is that it has been accused of large amounts of water waste. Talk to me a little bit about that.
Yeah, I mean, our traditional cooling methods are very outdated when you look at where the technology has progressed today. And I know that big chip makers position themselves near water facilities to be able to do that. Look at that dependency, right? The waste of the water and then having to be, I call tightly coupled. And we need to decouple this because I think that in the construction industry, we have learned that, we need to understand how the person's going to live in the house before we understand what kind of house we're going to construct. And it's the same thing, traditional data centers, we build the data centers first and then we brought the workloads into the data center. So it didn't suit the workloads because the workloads were heterogeneous and they're growing and they're diversified. We see the patterns. Extreme diversity is observed in these workloads and in their patterns of input management, how they're tokenizing and whatnot. And so the traditional rack model doesn't quite suit itself to as this movement, this diversity. It's not adapting. And so we need an adaptable model. And when we think of adaptable model, we think about what kind of new cooling technologies can we bring to play? And then how does that play in the construction of new data centers? Like, should we have a separate power room where we can have cooling take place? And that can be because it's decoupled. We don't have to tear down the racks and rebuild the entire data center. We can just go into our power room and we can update the technology, we can move faster and quicker and leave the cooling to the experts rather than be part of that whole data center design in a way that doesn't actually meet the needs of the actual usage pattern of the data center and the workloads.
If you can eliminate the water wastage, and our two-phase cooling technology doesn't use any water at all.
That's right.
And it's closed loop. And so it'd be a huge savings for data centers from that perspective. Also making it easier to locate because now you don't need access to water.
That's right.
So that's a key enabler, I think.
Yeah.
The other thing is, and you touched on this, it's how you design data centers.
That's right.
You've previously said to me that, homeowners are more worried about what the house is going to do for them, how it's going to be to live in the house, which is really how to operate.
That's right.
If you take that analogy to data centers, then data center owners should really be more focused on function.
That's right.
And less focused on things like what foundational technologies are you building into your data center, right? And so the architects of homes are not the engineers who actually solve the problem. The architect comes up with the vision of what they want. The engineers have to then create it, and the contractors have to build it. And I think we need to see something similar in the data center world.
That's right.
We need to see the use case for what the compute loads will need.
Yes.
We need to see provisioning of the right type of power, the provisioning of the right type of cooling, and then let other experts figure out how to do all that.
That's right.
And I think it doesn't mean you have to tear down data centers today.
That's right.
It means you can build data centers side by side.
That's right.
And an exciting thing about our modular cooling technology is that while you're building your data center, we can build a modular data center side by side
100%.
that can be operational in under 12 months
Yes.
while you build your more sophisticated, large-scale hyperscaler data center.
Yes. Yes.
And marrying these two data centers together
Yes.
gets back to the concept of us being able to orchestrate and manage power.
Yes. 100%.
Because while the data center is being built, they have very little need for power.
Yeah.
And as they begin deploying, they'll have more need for power.
Yes.
And that marriage of our dispatchable workloads together with the varying needs
Yes.
of consumption of the workloads on the hyperscaler or data center side
Yes.
become this perfect
And
connection.
it allows you to add on, it allows you to give that dynamic adaptability, ability to adapt right? As the growth happens, it's not a monolithic siloed structure, right? The other thing I was thinking about is with the MARA technology and the immersion cooling, the newer technologies. Remember how we were so attached to the phone because it was a landline, a physical landline, and we had to have a house, and every house had to have a phone. This is the traditional, you have to have a data center near a location for water, right? Like this kind of dependency. And now we have a mobile phone, so you can have whatever home you are, it doesn't matter. You carry your mobile phone with you, right? And so MARA is also having this technology to break this codependency, right? And I think this codependency is detrimental because we want to be able to have this abstraction, which actually gives us greater flexibility, which actually gives us greater efficiency, and then reduces waste. So that is another very important component of what MARA brings to the table.
And another way to look at that is also, if you think about your traditional data center, you had a whole set of subsystems responsible for cooling.
Yeah.
With our two-phase immersion, you connect the cooling and the compute in the same box,
Yes.
which means you essentially have cooling at the edge.
Yes.
And you're able to take your cooling co-located with your compute. So you could take a traditional data center and you could start adding liquid-cooled compute to it without having to change any of the infrastructure.
And how powerful is that? You don't have to do remodeling to get the benefits of what you want to get with your cooling, right? And all of the waste. Right? I can't tell you how many times we've sat there trying to figure out sustainability requirements of these data centers, right? Because we talk so much about being green, and yet when we power these data centers, they are so heat intensive, right? And so sustainability goes right out the door. And so we think about these things, we think we can naturally incorporate sustainability as part of our design, as part of our thinking, as part of the data center without actually doing a lot of work after the fact to go after sustainability.
Absolutely. It's energy transformation and waste reduction.
Yes.
All in one package.
Yes.
Thank you, Janet. So appreciate you spending time. Looking forward to lots more of these conversations with you.
Thank you.